let's continue in 1.3 and talk about the properties of matrix algebra. So given these definitions above for the zero matrix, basically given the zero matrix, the identity matrix, definition of matrix, we have matrix multiplication, so we won't be doing that, but we're doing addition, so scalar multiple, and matrix addition. So given all of those, that's where these properties come from. So we're not really going to look at any sort of properties yet for matrix multiplication, except like the identity matrix, of course. Okay, so here's some properties. Okay, number one, if you have in the matrix A, so write all that down. So A, B, and C are M by N matrices, and then lowercase a, b are real numbers. Then 1, A plus B is equal to B plus A. And I won't write all these out this time, but what is that? What are you doing? So that's commutative for addition, which we already established there isn't commutative for multiplication. Then 2, this is A plus B plus C equal to A plus B plus C. So what's the thing here? What's the deal here? Well, you can't add all at once. You don't do it just three times, all three at once. You have to pick. You have to either add those two and then C, or add the second two and then A. So what's that called? That's called associative. So it's an associative property for addition. Then you have scalar multiple associativity, AB, so you can multiply N if you want to A. So that's associative for scalar multiples. 4 is the identity matrix, appropriately sized, of course. A, and then we already kind of showed that one. Well, no, we showed it with a specific example, of course, but that is true. That's kind of easy to show. So identity matrix, so it's not 1, right? It's the identity matrix times A, or A times the identity matrix is equal to A. All right, 5. 5 is a distributive for scalars. C times A plus B is equal to C times A plus C times B. 6, we have A plus B times A equal to A times A, or little a times A, plus B times A. So it's another distributive. It's just basically distributing the matrix to the scalar multiple. 7 is your additive identity. So A plus the zero matrix, usually you write it like that, Mn, is of course just A. 8 is the existence of additive inverses. So because each entry is a real number, there is an opposite number for reals. So if all of those entries are opposites and you add them up, you're going to get the zero matrix like that. So that's additive identity for matrices. And then this one says, so if this is the zero product, so B times A is equal to the zero matrix, then either, well, actually it's not either, then B equals 0 or A equals the zero matrix. Or they both could equal the zero matrix. So that's the typical either or both for math. So there's probably a few proofs in the examples to go through of this. I'll show you one of them. you basically break it down into the a sub ij stuff. So let's look at well, I was just going to do number 1, just to show you how that kind of works. So here you say proof. We will do number 1. And so let's let A, and B be matrices. I wasn't quite done yet there. So be M by N matrix. B by matrices. And we'll say A is equal to the matrix A sub ij. And B equal to the matrix B sub ij. Okay, so if you just add those, by definition, you get A sub ij plus B sub ij. That's by definition. But then, by the commutative property of real numbers, so by the commutative property of real numbers for addition, we can commute those because these are all real numbers, right? Those are real numbers. So those, you have that commutative property. So you commute those. When you commute those, it's totally fine because they're just real numbers. You get B sub ij plus A sub ij, which is B plus A. That's by definition. By definition of matrix addition. So that's the kind of thing that you do. You want to explain why you're doing it, why it works, if it's not like completely obvious, especially if it's a property you're trying to use, like you just talked about it. Okay, and so that's why those commute. That's why that works like that. So that's your commutative property. And then the next step is undoing it, going back because of the definition for addition. Okay, let's do transpose properties. So here's first a definition, then we'll do some more properties. So if A equals A transpose, then we say A is symmetric. Then A is called symmetric. That implies, if that's true, A, so that's just like a note here, that implies A must be square. So it must be a square matrix, n by n. Next is properties of transpose. 1, 2, 3, 4. I probably should go to the next page here. So this is properties of transpose. So A is a matrix, etc. So if you do A transpose transpose, you do it twice, pretty clear there, you got A back, right? 2, if you have A plus B transpose, this one's not as obvious, then you get A transpose plus B transpose, which means that that operation is, would be called linear. So if you can apply an operation across an addition, then it's a linear operation. Like if you did a square root of A plus B, so if you did this, you can erase this later. If you did the square root of A plus B, we know that's not equal to the square root of A plus the square root of B, because it's not a linear operation. But this one apparently can. Okay, so don't really need that. 3. You have C times A transpose. You can still factor out the C, so it's C times A transpose. And then 4. This one's not as obvious either. A, B transpose, so the product transpose. You have to actually commute the next B transpose, A transpose. We will show, I'll show you here 2 and 4. So we'll do 2 first and then 4. So let's look at the proofs of these. Okay, so number 2. So let's let A equal A sub ij and B equal B sub ij. And then let's just look at A plus B transpose. So you start on one side like this and you work to the other side. In between, you never want to state right away that it's equal to that. That would be assuming your conclusion. Do not do that. You want to apply a property here. So apply a definition. So we're just going to write it in this form now as an addition. So this would mean Aij plus Bij. That's just by definition of addition. Okay, so then when you add that up, you get A plus Bij transpose. And within each of those, you can commute. You can just commute that, which is just B plus Aij transpose. Oops, I did that slightly wrong. Okay, so hold on, erase all that. Let's do that again. So we've added them together. Now let's go ahead and do the transpose. So we're going to do that. That becomes A plus Bji. So we go ahead and do the transpose. So it's A plus Bji, like that. That's what we mean by transpose. Now, unpack this. I just saw what I wrote down there. Ji. Okay. Now, unpack this. That's what I mean. So spread that out and make that into Aji. So that's going to be Aji plus Bji. Right? That's just writing it as separated. And then by the definition of the addition, you can write that as Aji plus Bji. And then that's going to be A transpose plus B transpose. Okay, so what I suggest you do to test this, so test this with a 2x2 case. So set this up like this. So do a 2x2 case with arbitrary numbers. So write down, let's see. So write down A. So I'd go A transpose is A, B, C, D. And then say transpose. Okay, so that's going to be A, B, C, D. like that. And then do B transpose. So E, F, G, H. See what I mean by 2 by 2, but make it general 2 by 2? And so then you get E, F, G, H, like that. Now do A plus B. I don't need brackets there, do I? Okay, so do A plus B is equal to I do A plus B. So A plus B is A plus E, B plus F, C plus G, and D plus H. Okay, and then what's next? Do its transpose, right? So then do A plus B transpose. That's where you would need that sort of thing. So you get A plus E, B plus F, E plus G, D plus H. And then do the transpose. And we'll get A plus E, B plus F, C plus G, and D plus H. Okay, so just it's a C there, sorry. All right, so now keep rewriting that. That is A, C, B, D plus E, G, F, H, which is what? Which is A transpose plus B transpose. So I'm just expanding it out, right, with a 2 by 2 to see what happens. And it's like, oh yeah, it works, yay. Okay, cool.